Why do I want to run DSC? Why do I care about it? What can I get off of it? I've already sort of alluded to this. So I have a DSC curve. This is what my instrument actually will spit out for me. Temperature and CP of my protein. This will be in Kelvin. This will be in kilojoules per Kelvin. And we're almost always talking about a molar quantity of protein. Okay. And again, like I said, there's some initial heat capacity associated with the protein when it's folded up. We get this increase as we unfold it, and then we have some difference at the end. So the textbook is going to refer to this as CP with a superscripted F for folded, and this one here will be heat capacity with a superscripted U for unfolded. And again, like I said, this difference here is delta CP. Yeah. Delta CP is equal to the heat capacity for the unfolded protein minus the heat capacity of the folded protein. This is always positive. I don't do true false anymore for you guys, but when asked last year, will it be positive always? The answer was true. Yes, yes, it is. Okay? And you can approximate, you can put sort of a function to this baseline here. Okay? You can put a baseline on it. What the instrument will do is it'll give you a baseline given by, so the heat capacity of sort of the folded and the unfolded protein will be equal to, this F here is the fraction that are folded. Oops, CP folded. So the fraction that are folded times the heat capacity that's folded plus 1 minus the fraction. So they're either unfolded or folded. There's nothing in between. So whatever isn't folded is unfolded. Okay. Do I have another pen color? I don't have another pen color on me. This area under the curve here, between the actual change in heat capacity curve that you're getting off the DSC and the baseline, so the area sort of between the curves, is equal to change in enthalpy of unfolding. And so, I mean, you could do the math if you wanted. You could estimate really small areas over and over and over again and sum them all up and get some area of approximation. We just let the machine do it for us and tell us what that area is. Okay. So here's our melting temp. Okay. Recall that heat capacity is equal to dH dt. And change in enthalpy is constant pressure heat flow. This is why, since we're measuring off of this instrument, we're controlling, we're looking at what is this change in heat flow rate to keep the temperature the same between our two samples. I can get a relationship to change in enthalpy, okay? And I can get delta H. So where it starts to unfold, or the first protein unfolds, same one. This is some T1. And then when they're all totally unfolded, there'd be some temp T2 where they were totally unfolded. And if I were to integrate from T1 to T2, with respect to temperature, and I have heat capacity for unfolding here, it would be equal to delta H of unfolding. Okay. The way to think about this is it is the heat absorbed by the protein in order to unfold. Okay. How come I can get standard state? So if I draw this little here and I have standard state, what do I need to do with my experiment so that I can get delta H of unfolding for standard state? So I'm already at 1 atmosphere. I have control over the temperature rate. That's not important to me. But what was the other piece of standard state? Say it louder. 1 molar, okay? We can control the concentration of protein in our DSC sample pan, okay? Such that we can get delta H of unfolding. So we can get the standard state case by just controlling what concentration we put in. Okay, and the standard state is 1 molar. Okay. So this is a part that's a little bit confusing. When I say I'm calculating standard state enthalpy of unfolding, this is at the melting temperature. I know, I integrated between 2 temperatures about the melting temp. So what does this mean? First and foremost, this is change in enthalpy of unfolding about the melting temp at the melting temp. This is not multiplication. Don't multiply these together. That's not right. Please don't do that. Okay? What I'm saying is standard state is going to let me figure out what my melting temperature would be, because delta G of unfolding at the melting temperature would be equal to 0, would be equal to delta H of unfolding, again, at the melting temp or about the melting temp, minus Tm times delta S of unfolding. And then I can set this equal to 0, and I can solve for change in entropy of unfolding, again, about the melting temp. Let's put this to define what temperature we care about. Okay. The H of unfolding divided by the melting temperature. Okay. We're not always at our melting temperature of our protein. Sometimes we're at some other temperature of interest. Almost always we might be at a different temperature, especially if we let standard state be 298 and our body is at 310. Okay, so those are 2 different temperatures. So we can think about, how do I get change in enthalpy or entropy of unfolding when I'm at any other temperature? And what this talks about is protein stability. So as I raise the temperature, at what point does the protein spontaneously unfold? And also, if I lower the temperature, will I reach a point where the protein will spontaneously unfold? And while it's a little bit counterintuitive, the answer is yes. I'll show it in a second. There is a point, it's called cold denaturation. There's some temperature below which the protein would spontaneously unfold. And there's a temperature of maximum stability. Okay. So, like I said, even though we integrate around the melting temp and we say, okay, this is our delta H of unfolding about the melting temp, we can then also look at other temperatures. We could just sort of shift where this curve is. I know it's a little confusing. Okay, so to talk about other temperatures, okay, and remember, this was 0 here. It's that piece over there. I suppose I could rewrite it down. From going from folding to unfolding at the melting temperature, concentration of folded is equal to concentration of unfolded. K would be equal to 1. Delta G would be equal to negative RT, the natural log of 1 equals 0. That way everyone has it when I post it. Okay? So like I said, I can't go through the proof. I can't talk about this in more detail because of time, but if you look at box 10.2 on page 450, okay, if you're interested in the proof, what we can then calculate, we have sort of this information available to us. We are, in reality, going to be interested in changes in enthalpy, entropy, and free energy at non-standard state temperatures. So delta H of unfolding at any temp, okay, is equal to the enthalpy of unfolding at the melting temp, my standard state sort of condition, plus the difference in heat capacity, and this is this delta Cp up here, the difference in heat capacity, times the temp I'm looking at minus melting temp. And for delta S of unfolding, at some other temperature of interest, I have delta S of unfolding at my melting temperature plus delta Cp, the natural log of temperature over the melting temperature. These two things here are corrective terms to account for temperature dependence. Oops, pretend that says dependence, of delta H and delta S. Okay? Delta H and delta S are not actually constants across all temperatures. Yes?